Okay, so it's modeling that like the cabinet design and the drivers and the rest of it, right?
Yeah, exactly. And then putting that into an environment and kind of modeling how that whole thing interacts.
Hey everybody, Dave Lindbergh in Hong Kong with another episode of the THD Podcast. Thanks for subscribing and thanks for tuning in. So today we got a company out of Iceland called Treble Technologies. We've had them on before a couple of years ago. We're going to find out about their lightning fast platform that lets engineers they simulate and hear things before they actually start building. So we're going to find out how that actually works for like buildings and cars and other environments. But without delay, let's thank the Alti Association, our sponsor. They'll be at the high-end show in Vienna next in June. And also Audio Express, always thankful to Joa for his support of us and all the technologies, including Treble. So if you like what we're talking about today, we'll put some links below in the description so you can go find out more about this technology. So today we got a guest host from Philippines, Colin Ward. Thanks, Colin, for stepping in.
No problem.
Okay, and Finnur Pind coming out, the CEO out of Iceland. How are you doing today, this morning?
I'm doing very well, thanks. Great to be here.
Cool. All right, so we actually got to meet in person at the CES at a nice, classy place, dive bar.
Exactly. That was
So,
a great event. Kind of if you want to get out of the sales and noise and so on, and just wear a band T-shirt and come to a bar with audio nerds, come to this event. That was perfect.
great. All right, so yeah, let's get into a presentation and update people on what you guys have been working on then.
Yeah, thanks for that. Happy to walk through that. So let me share the screen here. All right. So we in Treble, we describe ourselves as a simulation and data layer for audio AI and sort of acoustic virtual prototyping. I'm thinking maybe to spend 1 minute on kind of the backstory of how Treble came to be. That can be a nice kind of intro into how this all came to be and how the evolution has been, because it has evolved quite a bit over the years. And then kind of dive into the presentation and show exactly what we're working on these days and so on. So the roots, I'm one of the founders of the company. I'm a lifelong audio nerd, I suppose, as probably many of us are, and in this field, playing a lot of music back in the day, wearing a lot of band T-shirts, and and of course, the original plan was to become a rock star, but somewhere along the way, reality kicked in, and and I kind of did my plan B, which was a career in engineering. Ended up studying what's called acoustics engineering, the engineering of sound. Met my co-founder, Jesper, during those studies. This is almost 15 years ago now. We then go into two totally separate industries after our studies. I'm actually in the building sector, kind of an acoustic consultant. Jesper is in consumer electronics. He's working on hearing aids. And we both feel in our totally separate industries that there's a lack of good simulation tools for sound and acoustics. Not to say that there was nothing on the market, but we saw that there were certainly some areas for improvement in these totally different industries. I then get the opportunity to go back to school to do a PhD on really researching this topic and developing simulation technology for sound and acoustics. I'm really fortunate to get during those years to get to work with some great scientists, and both in acoustics, but also in numerical methods and GPU programming and so on. So we end up with a really promising prototype of a simulation engine that could simulate sound and acoustics much faster and more precise than what had been previously possible. This is then end of 2020. Me and Jesper reconnect, and we decide to start a company around this kind of core engine, converting it from a sort of an academic prototype into a real product. And the goal at the time was, we want to be this virtual prototyping tool for acoustics and audio. So if you're designing acoustics in a building, if you're designing the performance of a sound system in a car, you're designing, an audio product like a sound bar or hearing aid or something, you'd use Treble to simulate the performance, you'd iterate on your design and so on. And this certainly remains one leg of the business today, what I would call virtual prototyping, of acoustics and audio technologies and so on. But then sort of maybe around 2022, we started getting a lot of inbound inquiries on whether one could use our simulation technology, not just for this virtual prototyping, but actually to run thousands of simulations to create data that you could then use to train or test some kind of machine learning or AI technologies relating to audio, speech processing, or a variety of sort of machine learning based signal processing algorithms. And today, this is sort of our perhaps main area of business, this kind of data use case, of using simulations for data to develop audio AI. So that's kind of the whole backstory on how we got to where we are today. So I hope that puts us on the same page here in the beginning.
Okay.
Any questions on this before I dive then into the slides and so on?
I'm good.
Right now.
Not sure I fully understand it, but I'm going to refresh my...
Hopefully it'll become clearer. So yeah, in this presentation, I'm going to bring up the pointer here. Just give a brief intro around the company, talk a little bit about our simulation technology and show some benchmarks, and then perhaps especially elaborate on this kind of AI use case and data generation use case and so on. Give some examples of how that can be used, and finally show some benchmarks of how this higher quality simulation data leads to better AI performance or machine learning performance.
Okay.
So yeah, I guess I covered quite a bit of this already. We were founded in the end of 2020, team of around 35 people, and we specialize in large-scale acoustic simulation and audio data augmentation and spatial audio. And this is sort of an overview of our platform. We essentially have two products on the market, one which we call the application and one which we call the software development kit or SDK. These are essentially two different interfaces to the same kind of simulation engine that sits in the cloud. But there are quite sort of different use cases to these two products. So this one here on the left is a GUI software. It actually sits in the browser. And this is mostly used for acoustic consulting use cases. So maybe you're designing, the acoustics of a building or a sound system in a train station or PA system or a large system in a stadium or something like that. And you would have your 3D model of the environment in the application. You'd be running simulations, optimizing the design, maybe changing materials of the environment, changing the sound system properties and so on until you kind of reach your goal or your desired performance.
Is it like there's templates of like we've got like a cement built train station and we're putting this kind of amplification system in there? Like is it like a true GUI where you're kind of dragging and dropping like elements into it and then you simulate how it's going to behave?
Exactly. So, yeah, exactly. You would, maybe you can think like you have two screens here in your office. On the left screen, you have your building modeling software, where you have the 3D model of the building. And on the right screen, you have Treble. These two, they talk together, and you have material properties. You have obviously the sound system properties. You have some other input parameters. Then you simulate. You get back results, whether it's description of the acoustics or speech intelligibility, or there are some different parameters that you can analyze, and then maybe you change something.
If you're modeling like a live stage performance, would it also, as well as the building, does it model the effect of the audience? If you've got 50,000 people there, does it kind of model that too?
Absolutely. And then you could for example, compare how does this venue sound, with and without the audience, or whether it's half occupied or full occupied, and so on. Absolutely.
Okay.
Yeah. And then you can even one thing is to get out sort of objective measures, like maybe heat maps or some metrics and so on. But you can also just do these listening experiences where you can kind of step into the virtual, representation, listen to how it sounds, maybe compare on the fly, okay, if I have this material versus that material, or that sound system versus this one, how does it actually sound in that room? So that's pretty cool.
Yes, it's very.
And on this side, we've sort of really emphasized a few things. We've tried to make the whole workflow as efficient as possible, so you can really kind of rapidly do these simulations, do iterations, and so on. So that's one of the key value propositions. Certainly on the accuracy side, that's also something we've put a lot of effort into. I'll come back to that in a second. Trying to make the simulations as real as possible, and then a lot about these listening experiences as well, trying to make them authentic. Okay, this one here on the right side is not a GUI software. It's actually more a programmatic interface. It's a Python interface where you can be programmatically setting up simulations and doing all kinds of processing of data, essentially. In a programmatic interface. And this is then much more used for kind of development of audio machine learning algorithms, also of audio products.
Right.
Yeah, and it kind of lends itself very naturally to those kinds of workflows and fits into those kinds of pipelines and so on.
When you say audio, if I'm developing an active speaker, a studio monitor, I can model it in that to what it's going to sound like.
Yeah, exactly.
Interesting.
And you can test it in different environments. You can be modifying either the design of the loudspeaker itself. You can modify maybe some algorithms that are running on the device and test that and so on. Yeah.
Okay. So it's modeling that, like the cabinet design and the drivers and the rest of it, right?
Yeah, exactly. And then putting that into an environment and kind of modeling how that whole thing interacts.
Okay. Interesting.
Yeah.
And
go ahead, Dave.
It's just truly big data. Like the infinite number of elements in the equation here is kind of mind-boggling, especially go to theater size systems and then all the materials and people. It's a lot of data. Anyways.
Absolutely. And then, oftentimes, I mean, if let's say you're developing, smart glasses, which is a very complicated audio device. You're developing maybe some speech processing algorithm that runs on the device. Then you want to simulate, the design of the device, and not in just 3, environments, but in 10,000 environments, so that you've kind of built up a large data set of, how this device interacts with all kinds of different conditions. And then you can use all that data to develop maybe some, like I say, some denoising or speech enhancement or something like that. So it can be quite large scale, like you say.
Okay.
Okay, so this is the big picture view. I actually decided here today to focus a little bit more on this one. It's kind of more closer to audio technology and so on. So I thought maybe that could be more interesting. Just to make it a little bit more tangible, we can see a quick screenshot from each of the 2 products. So this is the application that we're seeing here. What we're looking at here is a model of a train station. And we see sort of a fairly large scale sound system in the train station here. Mm-hmm. This is a quite typical task for an acoustic consultant, for example. So optimizing the design of both the sound system and the train station itself. Sometimes it's just one or the other, and sometimes it's the 2 in tandem. And maybe trying to reach a certain level of speech intelligibility, so making sure that you can actually hear what the PA system is saying. Mm-hmm. So we see some color map result here, is looking at the sound pressure level in the environment with some particular loudspeakers, in the ceiling, and comparing different simulated conditions and so on. So that's kind of a typical use case as an example.
Yeah, you can see the Tannoy if you've got really sharp eagle vision.
Yeah, exactly. Yeah. Okay, but the SDK, I mean, like I said earlier, it's a programmatic interface, so that looks more like this. It's essentially Python code that you're using.
Okay.
Okay, if we peek a little bit under the hood for a second, this is one of our kind of main contribution is kind of a new way to simulate sound propagation in 3D environments or acoustic propagation. So kind of throughout the years, many methods and so on have been proposed, but usually they're grouped into one of these two buckets. On the one hand, there's something that's called geometrical acoustic simulation, where the sound wave is essentially approximated as a ray that sort of bounces around the room. That can be a very computationally efficient approach, but the accuracy can suffer in certain scenarios because in reality, sound doesn't always behave like a ray, it more behaves like a wave. But it's essentially a high frequency approximation. So at high frequencies, it's quite good, but at lower mid frequencies, it's often not very good.
Is there like a threshold where it's effective?
It depends a little bit on the use case, of what you're trying to do with the simulation. So in some scenarios, it can be quite acceptable to use this for, let's say, the majority of the spectrum. In others, it's not really good enough. So yeah, bit of a boring answer, but the answer is it depends. Yeah. So I would say, just to give a little more color, for example, if you have large environments, then this tends to be more acceptable. If it's kind of more open environments, that's also making it a little bit more favorable for this. If you have smaller environments, if you have, complex furnishing and, waves bending around obstacles and so on, then this kind of starts really to break down.
Yeah.
Okay.
The other approach is has pretty much the opposite pros and cons. So it's what's called numerical methods, where we're really kind of taking the physics equations of sound and solving them using computers. This is a very accurate approach. Captures diffraction and phase and scattering and everything. But it's computationally more heavy, especially if you go to high frequencies, because then you need like very fine discretization really of the problem. And kind of Treble's contribution maybe is twofold in this regard. On the one hand, we developed a really efficient wave-based or numerical approach, much faster than what had been previously possible. That's sort of a combination of some clever math, essentially clever acoustics, and also kind of really good utilization of computer hardware that made that possible. So we really kind of made it possible to use these kind of simulation approaches in larger environments and for a broad range of frequencies. The other contribution was that we also kind of introduced this hybrid approach where you can actually use both engines kind of simultaneously, where you cover a part of the spectrum with this one and a part of the spectrum with this one. That's a very good bang for buck, So that's the underlying core simulation technology.
Okay.
Interesting.
All right. Our customers are then, now I'm kind of zooming in on the SDK tech product AI side of things. So if we leave a bit the acoustic consulting out of it, then we have customers from a few different sectors, quite a bit within voice AI, where they're developing voice algorithms, making them more robust in real world conditions and so on with our data. Quite a bit here in audio hardware, like we touched upon earlier. Quite a bit here in automotive as well, simulating kind of interior acoustics and sound systems in cabins. And then some exciting emerging domains like robotics, which I'm quite interested in. Think about how much us humans rely on sound for situational awareness and communication and so on. And certainly the same will apply for robots when they come. And to develop kind of, let's call it robotic hearing, you need good simulation capabilities, you need a lot of data and so on. So that's a quite exciting emerging opportunity as well. And we have some 150 organizations on our customer list right now, including several of the big tech companies, some large audio tech companies, and automotive OEMs and so on. So it's quite exciting times.
Okay.
Yeah, I guess I'm kind of maybe going quite into the details, but this is kind of using simulated reality to test, train voice systems, audio processing algorithms, audio devices, fitting that into machine learning workflows, enabling people to rely on simulated data instead of real world collected data to improve performance of speech recognition and various other audio features that typically run on these devices.
Right. Yeah.
Okay.
I'd be always curious, like, because there's, I mean, I guess at some level, Comsol might be a competitor to you. And I was always like, I've always seen that Comsol could probably get 95% of the way there. And then you still got to build a prototype. And then it seems like
Right.
you get 95% of the way there with simulation in a month, and now with AI tools, like a month. And then the next 11 months, it's like these hardware iterations.
Right.
Are we still there with Treble, or are you going to be able to accelerate that? Because that's always the thing. Customers come to me, hey, which factory could build this for me in 6 months? And I'm always minimum 1 year, or go find somebody else to suffer through.
Right. Yeah, I mean, indeed, I think simulations can be a super powerful tool in the toolbox, but maybe it doesn't completely eliminate the need for physical prototypes and measurements and so on. It's more like complementary. It allows you to test concepts early in the design process. It allows you to test a variety of ideas, and then you sort of maybe kind of once you've sort of honed in on a particular design, you build a prototype and so on.
But
Same.
have your customer base, have they seen a reduction in that hardware iteration cycle by using your tool?
Absolutely, absolutely. Both for exactly the hardware design and certainly also on the data side, you can either go out and do a lot of measurements essentially to kind of collect real world data, or you can use simulated data. And we view it similarly, that we kind of augment the real world data. We maybe don't fully outright replace it. It has its place, but we kind of augment it.
I mean, in speech recognition, when you're saying it helps to develop the models there, does it also cope with like the regional accent variations? I mean, I did spend a lot of time in Alexa and Google, and the biggest problem always was English isn't English.
Right. Exactly. So you can kind of set up, a lot of scenarios, both across environments, across devices, across noise conditions, and certainly across, accents and languages and so on, and kind of build data sets that spans all of this to make it robust, essentially.
Interesting. Having sat with Chinese engineers for 6 years, listening to them trying to trigger Alexa, this would have been great.
Indeed. So progress is coming on that front. Yeah. And I mean, you mentioned Comsol earlier. Just a quick comment on that. We have tremendous respect for Comsol. It's a great product. We sort of try to view ourselves as being complementary or sort of solving a little bit of a different problem than Comsol does. So we're more on this kind of scale aspect, running lots of simulations and doing data sets and so on. Whereas they're kind of maybe a little bit more on the sort of, let's say, the inner workings of the device. That's kind of their specialty.
They're also like a general tool. I mean, it could be aerodynamics or multiple applications that they cover. So you guys are kind of application specific, it seems.
Absolutely. And really doubling down on the audio and acoustic use cases. Yeah.
Okay.
All right. So I guess we've, to some extent, touched upon this already. I mentioned 4 use cases here. Quite a large one is this idea of running lots of simulations to create large data sets. Yeah, I guess we've pretty much covered all of this by now. You can have different types of sound sources, maybe different types of human talkers, different types of HVAC noise, different types of loudspeakers, etc., different materials, kind of spin this all up. And that's, of course, also the power of the cloud, that you can really spin up a lot of simulations at the same time and so on. And then this data is taken and used to train machine learning models. I have some examples a little bit later of showing some results on how high quality simulation data can improve than speech recognition, for example.
Right.
That was for the first use case was kind of for training purposes, let's say, but then there's certainly also on testing how machine learning models perform, whether it's a model that's supposed to recognize speech or maybe localize where a speech, where a certain sound is coming from, like direction of arrival algorithms, or estimating how far is it to the sound source that is talking here, and so on. And then you'd want to test, how does this model perform in a variety of different conditions? And with using simulations to do that, then you can really kind of test, thousands of conditions really, and make sure that your resulting product is kind of robust across and generalizes, let's say. So that's a common use case as well. Third one is more on the hardware products itself, maybe optimizing microphone positions on smart glasses or loudspeaker driver configuration in a sound bar or what have you. And then the fourth use case I mentioned here is on this robotic hearing, which I think is quite interesting and sort of coming. So that's fun as well.
Yeah, definitely coming. I was at a factory and they were a big factory, 10,000 employees, all kinds of products, and they built 15 robots last year. So it's so like the component vendors can't get too excited about it yet, but who knows where it's going to go? Yeah, so
yeah. At least there's a lot of momentum in this space right now. It's kind of physical AI. So it'll be exciting to see how it unfolds.
Right.
I'm at least a kind of firm believer in that sound and audio will be a pretty large component here, for
Sure.
Yeah.
It's the natural interface with a human, right? So it has
right.
to be.
Exactly.
Yeah, the last time I stayed in China, I was chased around the lobby by a robot, which is quite interesting.
Yeah, that's actually, maybe people don't know, but like I always stay at the Holiday Inns in China, and they always have robots going up and delivering room service. Like for the last 3 years, this has been going on. So it's waxing over here, and also cleaning robots are in office buildings everywhere.
Yeah, indeed. Okay, couple of benchmarks here towards the end of the presentation. First, a couple of benchmarks on sort of, on the simulation technology itself, and then a couple of benchmarks on like these downstream tasks, of improving speech recognition and things like that. So this is a sort of, let's say, a rather isolated case, a controlled scenario, but still a quite interesting one. So there's a loudspeaker here that emits pulse, essentially. There's a direct sound that reaches on the microphone here, and then there's a single reflection of this sort of fairly complex surface here. And this is taken from a database called the Benchmark for Room Acoustic Simulations. So it's kind of an open source measurement database that is used to benchmark these kinds of technologies. And if we first turn our attention here to the right, and the black curve here is the measured frequency response between the source and the receiver in that condition. And then these are a bunch of different geometrical acoustics simulation tools that were available on the market in 2021, I believe, when this paper was written with around this measurement database. And we can see here that all of these simulation tools are not really able to model this particular scenario in the kind of low mid frequency range, because geometrical acoustics, maybe you remember we were talking about that earlier, these kind of ray based approaches, they don't do a very good job of modeling diffraction and detailed geometries and so on, phenomena that will happen when a sound wave hits this kind of surface.
Yeah, I think
that's not just sorry, go ahead, Dave.
I was just saying it would run out of energy before it hits the receiver, depending on the complexity. Just from a simple kind of point of view, like throwing a ball, eventually it stops bouncing, and so it doesn't reach the microphone.
Exactly. And I mean, this is not to say that geometrical acoustics are completely useless or something like that. There are definitely areas where they're perfectly acceptable and can add a lot of value. But at least if you want to model like detailed response where there is wave phenomena happening, then it's not really a good approach. Whereas, a numerical simulation will do a really good job of this kind of scenario.
Right.
Okay, if we then go to a more kind of full case, let's say, this is a room here in the outskirts of Reykjavik. We excite this room with a typical studio monitor, and then we measure in the room. We measured actually binaural room impulse responses. So we had a mannequin in the room with microphones in each ear. And then we try to recreate this scenario in simulation. So here we need to obviously take into account the room. It was actually furnished. So this shows the room empty, but it had, a sofa and tables and, typical kind of living room conditions. There's a loudspeaker that has certain characteristics that's radiating into the room, and certainly also the kind of receiving end of the simulation, with the head and the ear pinna and everything taken into account. And we want to try to replicate this as accurately as possible. And this is an example of a result we see here. So somewhere in the room, this mannequin, is, and we're looking at the impulse responses in the two ears here, and we see a very good match between measurements and simulations. Not 100% overlap, there's always some uncertainty with the material properties and the input data and so on, but still a very good match, in my very unbiased opinion. And being able to recreate these scenarios with simulation opens then up a lot of opportunities for virtual prototyping, for testing, for trying different concepts and so on.
Okay.
This is the time domain result. Then if we look in the frequency domain, we also see kind of a quite nice match, for example, these comb filtering effects here at the high frequencies and so on.
Okay.
Here's another scenario, which is even more challenging, you can say. We have the loudspeaker here in the mouth and the microphone really close by. So this is kind of what's often called an own voice scenario, which is, for example, very relevant when developing earbuds or smart glasses or things like that. And being able to simulate this with high precision. Here you have near field phenomena, which is, complex acoustics phenomena. And overall, we see a quite good match in this case, the mannequin being in the room. So we're both taking the room into account and certainly the head and the ear and everything.
Right. I mean, look, in the frequency domain, it looks like the biggest differential is at low and high end of this band, right? Is that what you expect?
Exactly. So this discrepancy here can probably be explained by the fact that in the measurement, there's this ear canal here, but in the simulation, we actually simplified the geometry a little bit. So the ear canal isn't present. So we should have actually blocked this ear canal when we did the measurement. So that's at least our hypothesis here. Low frequencies here, measurement uncertainty is quite significant. So that can explain something, maybe also about something about the loudspeaker properties and so on. Yeah. But this is certainly the challenging areas in general, you can say, both the kind of very low frequencies and very high frequencies.
Right.
All right. That was kind of the validating, let's say, the simulation technology. Now, how does this fair when we start running lots of simulations to create data. So here's a very interesting study our ML team did. So this was they took a kind of an established speech enhancement model from the literature. It's called Spatial Net, and they trained it. They trained it on, like, let's say, simple simulation data. That's sort of the industry standard approach before Treble came along. When I say simple data, I mean, it's both using simple simulation methods, only geometrical acoustics. It's using very simple rooms, kind of empty shoe boxes, and so on. Whereas in Treble, we'd simulate with detailed geometries. We'd simulate the device because it's like a multi-channel, like a smart speaker device that's running this speech enhancement model. We simulate the device more precisely. And so it's just kind of more detailed physics in the training data, let's say. Mm-hmm. And then our hypothesis was, of course, okay, I mean, more physics in the data has to mean that the model kind of fares better in real world conditions. And we're glad to see that was the case. So we're seeing some quite nice reduction in word error rates in the speech recognition model here. So that was exciting.
Yeah.
Good.
This was multi-channel speech enhancement. Here's a different type of study where the goal is kind of direction of arrival. So estimating from which angle a sound is coming from. Again, kind of training on different types of synthetic data, where the kind of high fidelity data leads to best performance, lowest localization error. This is a single, I just showed multi-channel speech enhancement. This is a single channel speech enhancement. This is a metric of perceptual evaluation of speech quality. So it was quite nice increase in that when using higher quality training data. This is a distance estimation task. So how far is it to the sound source that is in this scenario here? And then again, kind of nice improvement. In the final case here, maybe a bit of an academic exercise, but quite interesting still, where the goal is, it's a model maybe that's running on a smart speaker. It's supposed to predict what is the acoustic conditions of the room I'm currently placed in. What are the absorption properties of the walls around me, and so on. And we saw a very nice increase in kind of estimating these absorption properties when trained on better quality data. Mm. Oh yeah, and then I forgot about this one. So this is actually the last thing I want to show. So with all these benchmarks were around training. So creating data to train a model to do something, whether it's speech recognition or localization or whatever. But we briefly touched upon the use case of evaluation instead of training earlier. Mm-hmm. And the gold standard today is to evaluate performance on measured data. That's for good reason. That's kind of real world conditions. But it would be attractive if you could evaluate on simulations, because then you can test a wider range of scenarios. Because it's kind of time consuming and expensive to collect a lot of measurement data. So we constructed the study where we investigated, if you evaluate the performance of an algorithm on simulations, do you get the same results as if you evaluate on measurement? Mm-hmm. So the study is kind of summarized here. We took measurements from some 5 different rooms in a lot of different positions in the rooms and so on. Then we took 3 audio algorithms. It was like a de-reverberation algorithm, localization algorithm, and I forget which the third type was, but it was like 3 common audio signal processing algorithms. And we evaluated their performance on the measurement results and then on simulation results from kind of replicas of the physical environment, with 3 types of simulation approaches, ranging from like high fidelity simulations to medium fidelity simulations to kind of simplest simulations. Mm-hmm. And we then correlate, how does it compare? And we sort of saw, is maybe information overload here. Sorry about that, but we saw that if you evaluate on high fidelity simulations, then there's a very strong correlation with kind of what you get out as if you would evaluate on measurement. Whereas if you use simple simulations, maybe as you can predict, then the results are all over the place. So it doesn't really give you any insights into how the algorithm is performing. But this kind of proves the point that you can use high fidelity simulations to do your testing, and that in turn means you can test on a lot of conditions.
Right. Okay.
Yeah. So I hope I didn't go too deep here, but that's some insights.
Very interesting.
Yeah.
Okay.
Well, do you have any questions, Colin?
Yeah. So as somebody who does develop audio hardware, like not soundbars, but high fidelity or hi-fi, let's call it speakers, active speakers, streaming speakers. I mean, in the process there, when can I start? When do I start using this? Do I start this at concept before I either built anything or design? How does it give me a kind of insight into the workflow? What do I do to use this tool to develop my speaker and kit?
Yeah. So you can certainly start before having any physical prototype or so on. If you have some kind of drawing, essentially, or CAD of the device you have in mind, then you can import that into Treble. Let's take a studio monitor as an example. You have some design, some cabinet, some vents, maybe some drivers, and so on, and then you can really simulate that.
So the input data for the drivers, what is, you just put in the parameters, the F0 and all that stuff, and it knows what to do, or do you need a more detailed model of the driver?
You can use kind of, let's say relatively simple descriptions of the driver, but then also kind of if you want to go more advanced, you can do that as well. Yeah.
Interesting.
Yeah.
And are there people developing, like, I mean, there must be databases of every, MEMS microphone and every speaker driver so that they could create these systems virtually. And is there forums, or are there people contributing to a community to create these massive, I mean, the amount of data needed is endless. And, like things like, I always remember like materials vendors for like speaker cones, like the people, they go, what's the Young's modulus of this material? And they're like, well, we've never sold it for acoustics, so we have no idea. So I guess there has to be some people that are creating that data. There's value in that and time consuming. So I guess, creating this, because we interviewed somebody else that's coming out right away, or it should be already out by the time this is out, but they're using natural language to create their system architecture on a silicon chip. And so, where does, and it's pulling from the internet, like this is the architecture for a two mic karaoke system, and this is your real-time processor. This is how you have to architect it virtually. And so are you guys able to pull from internet resources to like get all the simulation data together? Are you seeing people do that?
Yeah, absolutely. So, and you're absolutely right. The input data can be quite vast and, spanning, whether it's the kind of 3D environments, whether it's the materials, in the environment, or the sound source properties and the materiality of that, or on the receiving end, different microphones and so on. We've done quite a bit of work on our end to kind of build a pretty nice database across all of these dimensions. So there's quite a lot that comes with the tool already. Also happy to share that we're kind of working with some of the larger sound system manufacturers, loudspeaker manufacturers, on building really kind of an open data format, for manufacturers being able to put out their data. We're actually both doing this on the loudspeaker sound system front and on the acoustic material front as well, building these kind of open data formats where people can share freely and any manufacturer, any vendor, any software can work with it and so on. So that's a really exciting development as well.
You can imagine it almost like an attachment to a data sheet. Here's the plugin to run this.
Exactly. Yeah. And our vision is that this should be open source, or kind of so anyone can work with it.
Okay. All right. Good stuff. Okay, let's table this for today. We'll put contact information below, and encourage everybody again, like, subscribe, and check out the Treble website for more details. And Finnur, thanks for joining us today. We appreciate it. Hope you had a good time.
Thank you for having me. Yeah, absolutely. It was a pleasure.
All right. So thanks, everybody, and we'll see you on the next one. Bye-bye for now.